So in this module, we'll perform a mole balance on a simple constant volume batch reactor. And draw a little schematic of a batch reactor. It's a closed system, and our batch reactor is going to be well mixed. And let's say at the beginning of our reaction, we have some A inside our reactor, and that our reaction is just simply A goes to B. So we're going to write our mole balance here in terms of A. And as always with mole balances, we're going to look at the rate in, then subtract the rate out, add the rate of generation, and this will equal the rate of accumulation. So in the closed system of a batch reactor, the rate in is 0, as is the rate out, so 0 minus 0, plus the rate of generation. And because this is a well-mixed reactor of constant volume, this will be the rate of formation of A multiplied by the volume. For a more complete lecture about rate, the formation, and rate laws, you can click on the screen now. And this is going to equal our rate of accumulation of A inside a reactor, which will be the change in the moles of A, which we denote Na, with respect to time. We can do a unit check here to make sure we're on the right path, and we know the units of Ra are going to be moles per volume times time, and of course the units of volume will be volume. And we know that the change in the number of moles with respect to time should be moles over time, which makes sense because our volumes cancel and our units check. So we have our differential form of our mole balance for a simple batch reactor. And if we want to solve for t, for example, we can just integrate this and get the integrated form of our mole balance. And to do that, all we do is solve the differential equation here. So we can rearrange the terms. Have dt equal to dna over Ra times V. Then integrating both sides, we just get that t, time, is equal to the integral from our moles of A to our initial moles of A of dna over Ra times V. And because the rate of formation of A, in this case, and in many cases, because A is generally a reactant, is going to be negative, oftentimes it's customary notation to use Ra as negative, so we can just switch the limits of integration and say this is equal to the integral from Na naught to Na of dna over minus Ra times V. And you can see it typed out a little more neatly here, but this is our integrated form of the mole balance for a simple batch reactor. Of course, we may be interested in the concentration of A as opposed to just the amount of A, especially because rates depend on the concentration of A, or the concentration of the reactants generally. So, because we know that our volume is equal to our initial volume, as it's a constant batch reactor, we can do some simple algebra here to put this in terms of concentration. And so we're going to multiply both sides of the differential form of the mole balance by 1 over the volume. So we have 1 over the volume times the rate of formation of A times the volume is equal to 1 over the volume times dna with respect to t. Of course, on the left side, our volumes cancel, and on the right side, because our volume is constant and thus independent of time, we can see that we're able to put our volume inside our derivative, such that we have the rate of formation of A is equal to derivative Na over V, all with respect to time. And recalling our definition of concentration is just the number of moles over volume is equal to concentration of A, we'll call Ca. We can see here that this just really simplifies down to Ra is equal to dCA with respect to time. These are the simplified versions of the mole balance with respect to A for batch reactions, and these are widely used when dealing with batch reactions. Here's what I've wrote out on the previous slide, just a little more neat for you guys.